Hello once again. Thank you for joining us. This is the Space Nuts podcast, heard across Australia and around the world. My name's Andrew Dunkley, your host, and it's great to be with you once again. And coming up on the show today, we're going to be dedicating the entire program to audience questions. We've got questions about satellites and the Earth's shadow, the speed and age of light, the interstellar medium, the non-existent luminiferous ether, and life, as well as quantum fluctuations. We're going to cover all those topics from our audience on the program today. We also have some news, which I think you'll find very exciting. So we'll get into that, but not before I introduce the great man himself, Professor Fred Watson, astronomer at large. Hello, Fred.
I was just thinking at the start of the show, it's amazing how you remember all the right things to do and start with introducing me, and then you didn't. And I thought, oh, he's forgotten. No, never mind. No, I'm here and lively and looking forward to our chat this morning.
Now, you're still in lockdown, and I am expecting sometime today that I will be too.
Join the club.
Because we've officially found a case of COVID-19 Delta strain in Dubbo. So it is here. And look, I'm hardly surprised. I know a bit more than people in the public know at the moment due to my journalistic connections, but I'm not able to say anything at this point in time publicly, but I'm sure the news will come out. But yes, there is a case in town, and the source is unknown, which is even worse. So I'm expecting any time now to receive lockdown orders. So join the club. That'll mean that every member of my family is now in lockdown if we get locked down today, and it looks like it's imperative, so or imminent. So here we go again, Fred.
Yeah. Part of life's rich tapestry, Andrew.
Yes, indeed. Yeah, if that's what you want to call it. Oh, dear. Yeah. Anyway, who would have thought at the beginning of last year we'd still be dealing with what we're dealing with now, and I don't think it's going to go away this year or into next year, and it might even go a lot longer than that. I think this Delta strain is with us forever, and that's very unfortunate. Anyway, we're here to talk about astronomy and space science and to answer questions from the audience. So without further ado, let's get our first audio question. Now, we don't know who this is from, but that's okay. The question will become self-apparent.
Hi, Professor Watson and Andrew. Thanks for such a great show and also answering my questions. Just to let you know, I have bought a Space Nuts sticker from your shop and plan to proudly put on the back of my car. My question today is about satellites, the Earth's shadow, and impacts on the night sky. I notice on heavens above by default that it only shows the satellites going over during the dawn or twilight hours. As I understand, this is due to the site showing only visible passes. From a technical sense, my understanding is that after the sun has set, the satellites no longer are able to reflect the sun's light, and thus being no longer visible. Could there be a situation where satellites are visible during the night hours? Can the satellites transit in the night sky and the Earth's shadow still be visible or impact ground-based telescopes? The reason for my question is about understanding the impacts of the satellite constellations on professional and amateur ground-based telescopes. There is much discussion around this at the moment, and a lot of articles in the popular media around the impact on our night sky. However, it's hard to tell how much of an impact there is or will be. Is the impact only during twilight and dawn hours, or could these satellites cause an impact any time of the night? On a side note, my brother recently passed away after a year-long battle with lung cancer. He was 43. He never smoked and barely drank, but was just unlucky. He got me onto your podcast, and I hope you don't mind me taking the time to note his memory. Thank you.
Thank you so much for your question, and very, very sorry to hear about your brother, and really glad that he put you onto the Space Nuts podcast and that you both got some great value and good times out of it, and probably had some wonderful discussions together as well. So sorry to hear about your brother. It's always sad news when something like that happens, especially under those kinds of circumstances, and I think we've all been there. Fred, let's talk about satellites and their visibility and their interaction with telescopes and the potential fallout from that, given that so many are being launched into space, into low Earth orbit, and some of the controversy surrounding that in recent times. Where do we start with this one?
It's a multifaceted one, and it's one that concerns us a lot in the world of astronomy and space science at the moment because of the influx of these mega constellations, which we're on the brink of seeing. So there's a number of aspects to this question. Let me just start with one, because it's the slightly off-field one. The satellites we're principally talking about here in the question are what are called near-Earth objects, near-Earth satellites. Low Earth orbit satellites, ones that are relatively close to the Earth. I think low Earth orbit is defined as up to 2,000 kilometres, if I remember rightly. But of course, there is another family of spacecraft at 36,000 kilometres, and they are the geostationary and geosynchronous satellites, which we rely on for communications. Now, they are so far away that most of the time they are outside the Earth's shadow. They're not within the Earth's shadow. They do pass through the Earth's shadow from time to time, but most of the time, most of them are outside the Earth's shadow. And that means that technically they are visible outside twilight. Now, against that is the fact that they're at 36,000 kilometres. They're shining by reflected light from the sun. They're small objects. So generally speaking, they are very faint. And I remember an experiment we did at the UK Schmidt telescope decades ago, where we actually photographed some of them, and they were like very faint stars. They were on the limits of detectability with that telescope. That's a 1.2 meter telescope. So generally speaking, you don't see them. However, some of them have these flat panel antennas on them, and so occasionally you will get what are called specular reflections from the sun. In other words, the sun hits one of these panels at exactly the right angle to send the beam back to Earth. And once in a while, you see flashes from geostationary satellites well outside the twilight zones. In other words, any time during the night. So that's a slightly different thing from what the question's mostly about. But that is a case where you can see them, at midnight or times like that. But generally speaking, it is true that excuse me, to the naked eye, the only time we see satellites is within about an hour or so. It depends on latitude, so it's not definitive, but within an hour or so at mid-latitudes of either an hour or so of sunset or an hour or so of sunrise. It's a bit longer sometimes, up to 2 hours perhaps. Outside those times, the satellites are dark. They're not illuminated by the sun, and they're essentially invisible. Although for professional telescopes, of course, they might occasionally blot out the light of an object, but they don't leave a trace. They don't leave a trail on the image because they are dark. So the effect is really very minor. Outside against that, once again, another aspect of this that's not necessarily obvious. As far as radio astronomers are concerned, these things are live all the time because they're broadcasting radio signals. Depends on frequency bands and things of that sort. But none of that applies in the radio spectrum. They're live all the time, and indeed they actually have the capability of reflecting terrestrial radio signals back to Earth. So that's one of the worries with the square kilometre array, that radio broadcasts from Perth and Geraldton might be reflected back to Earth by satellites passing overhead. That's why things like the Heavens Above site only show when these things are occurring during twilight hours, because that's when they're visible. Just one footnote is that SpaceX has been trialling what they call their visor sats, and these are basically dark screens that actually block the light from the sun from landing on the spacecraft in order to reduce their visibility. Now, the target that SpaceX has is to push the visibility of their satellites in twilight down below the naked eye threshold, so that we're not seeing a night sky with literally hundreds of satellites going past at any time. That we haven't seen any firm reports on the outcome of that, but the discussion is ongoing, and it's part of certainly SpaceX. They are keen to try and work with the astronomical community to mitigate the effects of their mega constellations, but there's a limit to how much can be done, basically. The problem is the constellations themselves. There's so many of them. So an interesting question, and I hope that explains what's going on.
Yeah, I hope so too. But I remember as a kid often going out on the back patio at my grandparents' place and just lying down just after sunset and watching for satellites. Now, there weren't that many of them back then compared to today, but we used to get really excited when we saw this little speck of light just darting across the sky. And, we'd see other things as well. But it was a pretty exciting thing as a kid, and of course now they're a dime a dozen, aren't they?
If you're looking at the night sky after twilight, there's a good chance you'll see one, or before sunrise. Yeah, it's
and of course now you can track them on the internet, so you know where and when to look for things. And of course, the International Space Station, there's a website dedicated to where it is, and so you can easily pinpoint its location and go outside and take a peek, which I've done once or twice. But it's so much easier now. And back in the day, you just sort of wonder what that was, wonder which one that was. No idea. But is it going to get worse, Fred? Is that likely?
Absolutely.
In a word.
We've got the potential for there being 100,000 satellites in low Earth orbit. That's the number of mega constellations that are being proposed. So it is going to get worse.
Gee, yeah, reminds me of a bad sci-fi film. Okay, there we go. And thank you again for your question. Let's move on. And this one comes from North California.
Hello, Andrew and Dr. Fred Watson. Ralph in Northern California again. I posed a question recently about the speed of light, and it probably got buried in your multitude of questions. That one was, can photons ever go slower than the famous speed of light? With gravity lensing and other ways of bending light, I would think that at some point they might go a little bit slower. The second question is, how do we measure the age of light? If we say it's 2-point-something million light years from Andromeda to reach us, how do we know that? How do you guys figure that out? For that matter, how do we know it takes 9 minutes for light from our own star to reach our planet? I've always wondered about that. Anyway, great show. Always keep it up. Thank you, guys, and rock on.
Thank you, Ralph. Lovely to hear from you again. How do we measure the age of light? How do we know it takes that long for it to reach us? I'm thinking it's the thumb test. You lick your thumb and put your finger up in the air and go, it's 8.5 minutes to get from the sun to the surface of the Earth. It's probably more scientific than that, isn't it?
Yeah. Let me start with the first bit of Ralph's question about whether photons can go slower. And of course, the answer is yes, they can, because as soon as light comes out of a vacuum and into another medium, whether it's air or glass or water, it slows down. And that's why we get the phenomenon of refraction. It's that slowing down of light in these media that does the slowdown. So photons can indeed go slower than light. And there are some experiments, which I confess I don't fully understand how they do it, but there are some media that light can pass through. And when you do certain things to it, you can actually stop the photons and then let them go again. And that's a pretty amazing thing to be able to do. It happens in physics labs, a number of experiments that have succeeded in doing that. But, in the normal natural world, we see light being slowed down all the time. So that the speed of light being immutable is the speed of light in a vacuum. And that's the one that sets the speed limit. Nothing can go above the speed of light in a complete vacuum. And then the second part of the question, if unless you've got a comment there, Andrew. I heard you draw breath. Okay.
No, yeah, that's all I was doing. Taking
Don't
a breath.
do it. It's
Well, I suppose the second part of his question is about the
Yes,
age
that's
of
right.
light and how we determine. Now, because the funny, we have discussed how light is produced and how long it takes for a photon to actually get out of its parent star, and that's, I mean, light is old before it actually
that's right.
leaves the star itself, in the tune of tens of thousands of years, or is it more? It's a massive number.
The best estimate is 170,000 years. This is for the sun. But some scientists think it could be up to 1 million years. It's because that's a slightly different process, though, Andrew. What's happening there is, the nuclear reactions at the centre of the sun are producing photons, which are actually gamma rays. They're very high energy light. And those photons are, as soon as they're emitted, they immediately run into another atomic nucleus, and they interact with that and get re-emitted. And that process continues all the way up to the surface of the sun, with slightly less energy being released every time. And so when they leave the surface of the sun to take their 8-minute, 20-second journey to Earth, that means they're visible light. So that's a different process. That's because it's a different photon that comes to us from the surface of the sun than the one that was created in the center. Basically they interact with the atoms around them. But Ralph's question is a really good one, and it goes to the heart of how we measure distances in astronomy. And it's not by timing the age of light. That is a construct that we build after we know how far something is away. For example, the distance to the sun was first measured by measuring the parallax of actually the planet Venus. It's why 17th and 18th century astronomers went off chasing transits of the planet Venus across the sun's disk, which only happen rarely. They mounted expeditions to do that because by observing Venus crossing the sun's disk from two different places on the Earth whose separation is known, you can work out the distance to Venus just by what we call the parallax. It looks as though it's crossing the sun's disk at a slightly different place from each location. So you make those measurements, you do all that, and you calculate the distance of Venus, and then from Kepler's laws of planetary motion, you can work out what the distance is of the Earth from the sun. So that's how that works. So what you're doing is you're using geometric methods to measure the distance. And then you're saying, well, we know the speed of light. So light takes 8 minutes, 20 seconds to get from the sun to the Earth. That's how we know that light is 8 minutes, 20 seconds old. It's not a phenomenon that is measurable by the light itself. And that's how we build up our knowledge of distances, Andrew. It's similar processes. When it comes to stars, it's the parallax again, the fact that a star looks slightly different from one side of the Earth's orbit from what it does at the other side. So then you can work out its distance. Then you build up the distance scale by looking at standard stars. I used to work on a class of stars called RL-Lyrae variables, which potentially can tell you the distance to something because they've got a fixed brightness level, which you can measure by looking at the way they vary. The variable means that they vary in brightness. That gave us an early measurement back in the day of the distance to the center of our galaxy, for example. Then you look at other sorts of variable stars, something called Cepheid variables, which are rather brighter. And it was when Edwin Hubble measured those in the Andromeda galaxy that he was able to work out the colossal distance of the Andromeda galaxy, which we now know, as Ralph says, is about 2-point-something million light years. But it's because of all these intermediate steps that you can work out how long the light has been traveling. And on the largest scales, we use redshift. We use the fact that the universe is expanding, and that expansion reddens the light because the light waves are stretched. And we can calibrate that expansion by the Hubble law. or I think it's now called the Hubble-Lemaitre law because of Georges Lemaitre, who was the Belgian priest who figured all this stuff out alongside Hubble. That lets you work out the distance to these very distant objects. So in that sense, we are, that there is a property of the light that's telling you that it's aged, and that is that its wavelength has got longer. It's been reddened because of the expansion of the universe. But otherwise, other than that, we don't look at the age of light. We look at other distance measures and then work out what the age of light is. One other thing that I might throw into this is that to a photon, time doesn't exist. So they're all ageless in their own reference scale, if I can put it that way, their own reference frame. So photons are rather interesting. They don't experience time.
Do they end? I just wonder, when the light comes out of the sun and it does its 8-minute and 20-second journey and then hits the Earth, is that the end of the photon?
Yes, actually, it is and it isn't. What happens then is something similar to what happens in the centre of the sun. It hits another atom and does something to it. And in fact, normally what it does is it imparts some energy, which just very slightly heats up that atom. In fact, you've only to stand outside in the sunshine to know that you're feeling radiant heat from the sun. You're feeling infrared radiation, but also the light, to a small extent, is heating you up because it's converting its energy into heat energy within your body. So it does come to an end, but it turns into something else.
Okay, yeah. I'm just thinking, the photon pops out. And it sees Earth and goes, oh, damn it, I wanted to live longer than that.
Yeah, that's right. Some photons are, going for 30.7 billion years, nearly the age of the universe.
Yeah. Fascinating. All right, Ralph, hopefully we adequately answered your question about light and photons and the age of light. I find it all very fascinating, light and shadows. I really do. Thanks again for your question. This is Space Nuts. You're with Andrew Dunkley and Professor Fred Watson.
Space Nuts. You've been listening to the Space Nuts podcast.
Available at Apple Podcasts, Google Podcasts, Spotify, iHeartRadio, or your favorite podcast player. You can also stream on demand at Bytes.com.
This has been another quality podcast production from Bytes.com.